This works. Hi. Good morning. I don't know if anybody's with us, but we are about to start Science Saturday. Hope that everybody is happy and safe, and we are about to get started. Our favorite visitor scientist, Joe, is behind me getting everything ready. Hey, Joe. And I'm here, since I can't be at Lattes in Paradise, with my own coffee, with the same coffee that they use, the VI coffee roasters at Lattes in Paradise. So, we are about to get started.
Well, that sounds great. So, thanks everyone for coming. Today, we're going to be talking all about water, how weird it is, and why it's so different than anything else that we work with. Thank you, good sir. We are accepting donations. But anyway, so to start off, I think we want to just talk about how water is different from other liquids that we come across. And it has a couple very special properties about it that I think is really interesting. One of them, this is a classic example, just takes a penny. It's a shiny new one, 2018. Now, water itself, this is just tap water from my house. If we, it actually has certain properties in it that the water molecules that are within the water moving all around with each other are actually really strongly attracted to each other. And so they'll actually tend to stick to each other. That's kind of like that feeling when you get out of the water and you're still wet. It's because the water is actually just kind of sticking to itself and it doesn't want to just immediately leave you. And so one way we can demonstrate this, it's pretty cool, is we can take a little bit of water. So Kitty,
Yes.
I'm dropping water drops like that. 1, 2, 3. How many drops do you think that we can get on this penny?
Oh, I think that we can get, if that is 3, I think we can get 20.
20 drops. Let's try. Here we go. 4, 5, 6, 7, 8, 9, 10, 11. Let's get a refill here. 12, 13, 14, 15, 16, 17, 18, 19. Uh-oh, Kitty's gonna bust. 20.
Woo! We made it.
21, 22, 23. And if you look really closely, you can see how the water, even though it's maybe hanging over the edge of the penny, it's still sticking to itself. And for this reason, we can actually fit a lot more in this penny than we expect. 24, 25, 26, 27, 28, 29, 30.
Oh, gasp.
30 drops
30 drops.
onto a penny. Now, by comparison, if I take, let's say, for example, a little bit of, this is some oil that I use for cooking. This is some corn oil. We're just going to pour out a little bit of this so we can use that. And we'll notice that the oil, even though it's also a liquid, behaves pretty differently than water. While it's attracted to itself, it's not attracted to things like water. And so it's not as strongly attracted to itself. So it maybe won't have as much on the penny as we got for the water. Now, let's test that. The score to beat was 30, right?
Yes.
All right. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Oh, it's all the way around the outside now.
13. Oh, that was a bubble. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 4. Oh, wow.
This is impressive.
Whoop. All right. 25, 26, 27.
Oh, 28.
Well, yeah, 28, 27.
27 and a half.
Right.
That's fascinating.
Right, and this is because while the oil is attracted to itself, it's not as strongly attracted as the water is, so we probably can't get quite as high of a number. And I bet if I tried this a few more times, what you would see is that consistently we see the water staying on the penny a lot longer than the oil. And now while these things are attracted to each other, Here, I'm just going to put this right now just back in this over here. It's actually interesting to note that water and oil, while they're attracted to themselves, aren't attracted to one another. And this means when we add oil to water, although they'll kind of mix together at first, but we notice early on, they actually won't mix together at all. So we see, at first we have these bubbles, but then we see that all of our oil has come to the top of the jar. Meanwhile, our water stays in the bottom with a little bit of oil just kind of trapped down there by that same surface tension.
Fascinating.
And so this is really interesting. We can actually look at different liquids that aren't attracted to each other, and we can see how different densities of those liquids decide where they go. So, for example, if we add another liquid, such as dish soap, we can see how dense it is compared to the oil. So we're just going to add a little bit there.
Also important to notice, this is beautiful.
So one thing you'll notice is that the dish soap reacts with the oil and breaks it down. That's one reason we use dish soap when we're washing things. It's a specific formula that dissolves the oil. And so that it's going to kind of take in with this at this oil margin and dissolve it down to this more dense kind of residue. So hopefully you're not cleaning with this much oil in your pots and pans, because you would need a lot more dish soap than this to dissolve it all.
Yes.
Now, some fun things we can do acknowledging the cohesiveness of water. This is something that I saw online, so we're going to see how well it works here, truth be told. But what you have here is this is just 5 toothpicks, just kind of nearby each other, and note that when I touch them together, they're really not like sticking together at all. So, let's take some of our water. Let's grab a new syringe. Maybe. Oh, we can just rinse this one. So with a couple drops of water in the middle here, looks like the cloth is absorbing
Maybe we need to do this one in a container.
Ooh, good idea. Great idea, Kitty. Let's start with new toothpicks. Fresh, dry toothpicks. That way we have scientific
So if
rigor.
you want to do this, you can follow the instructions. You can see how Joe is breaking the toothpicks.
Just in half.
Super scientific for Science Saturday.
Of course.
Or whatever day you decide to watch this on.
That's the fun of Virtual Science Saturday. It can be any time you want. So I've just taken 5 toothpicks here, and I've just broken them more or less in half. Now, if we take our syringe, here's the other syringe. And now again, I'm just dropping the water in, not doing anything else, and you see that what will actually happen is these pieces will get drawn together more tightly than they were before. And that's because the water that's being absorbed into the wood pieces is actually still drawn to itself. So even though the fact that it's being soaked into this wood, it's still being drawn to its own molecules. And so we can use that to kind of hold this piece together and make our lovely star toothpick.
Ooh.
Very nice, right?
Drawn together.
Now, let's go back to talking a little bit more about the density of water. What do you think?
I think that sounds like a great idea.
Sounds like a great idea? Good, because that's what I had in mind. So, the density of water is the way that we can determine what things float and what things sink. So, if I take basically, things that are less dense than water will float. Things that are more dense will sink. Water, therefore, has a density of about 1. Depending on how hot it is, what's dissolved into it, all sorts of things can affect that density of water. So what we're going to do now is we can test what things will sink and what things will float and figure out what their approximate density is. Put a little bit out over here, just so we have room. So, what do you guys think? Float? Sink? Neither? Kitty?
I think it's going to float.
You think this is going to float. So this is going to float because it's less dense than water. All right, let's take it out.
Woo!
Nicely done, Kitty.
Thank you.
So, basically, however low this sinks in the water, that same buoyant force pushes it up because this is less dense than water. So, next, we have a fully peeled, I believe this is a tangerine, clementine, I'm not sure which.
Let's go with tangerine.
Tangerine, I think it's a tangerine. This is also a tangerine. So, a fully peeled tangerine. So, let's see if it floats in the same way.
Oh.
So
Interesting.
Right. So it looks like it has something to do with this peel. It's creating a difference in density such that this is less dense than water and this is more dense than water. So, what do you think would happen if...
Perfect. It's magic.
I don't even know how I did that.
Or is it science?
So now we have a tangerine clementine orange that is neither fully peeled or not peeled at all. It's half peeled. What do you think will happen to this density?
What do you guys think? I think we got to go halfway in between, right?
Seems like it would make enough sense, right? The fun of science is how much of a mess you make, by the way.
Oh, pretty floaty.
Yeah. Let's take this guy out so we can see for sure. Interesting, right?
Mm-hmm.
So it looks like the peel, it's not even just the whole peel, but even a little bit of peel can make all the difference in how floaty it is. What do you think will happen if we peeled this even more? Let's say to a quarter.
I think it'll float a little bit lower. Right, guys?
I would say that's about a quarter of the peel, right?
Mm-hmm. Ooh.
Still floaty.
Still pretty floaty.
What about an eighth? Oh, whoops. I think that's about an eighth of the peel. You can say no.
I agree with you.
I think it's about an eighth of the peel. Let's take a look. Still pretty floaty.
We are learning that this tangerine has very floaty peel.
Interesting, because when we remove it completely then...
What?
So one thing that tells us is that this is really, really non-buoyant. And we know that partially because this is made up a lot of different kinds of fats, actually. And fats, as we know, are less dense than water. Right?
Yes, we have a comment from the crowd, like a wetsuit. Thanks, Mommy.
Yes, so a wetsuit is something that's a lot less dense than water. That's why when we put a wetsuit on, and we have to wear more weight when we're scuba diving and things like that, that's absolutely true. And one of the reasons that a wetsuit is less dense than water is because it's really spongy, right? There's a lot of air within that. And so overall, the actual substance is less dense.
So we learned that oranges and tangerines are very floaty.
Indeed.
Maybe that's why they use them to study currents. Which could be a topic for another Science Saturday, where you throw all the oranges out and then it goes around on top of the water.
I mean, I just want to eat them, but...
Well, we're definitely going to eat them.
We could do either one. And so even water itself can actually have different properties that make it more dense or less dense than one another. And so actually it's a good point that wetsuits got brought up, because I think this is something we consider all the time in scuba diving. One thing that dive shops and different divers will note that when you're scuba diving in salty water compared to fresh water, you actually have to wear different weight. And that's because the density of the water itself is actually different depending on how much salt is in the water. So this one required a little bit of extra prep, thanks to Kitty Edwards, who has taken our water here, in addition to turning it a beautiful, wonderful blue color, has also dissolved salt into this. So you can imagine this is kind of like ocean salt water, the stuff that tastes great when you go to the beach. And then we have our regular water here. Let's go ahead and I'm going to put this into our waste bucket here so that we have room for this. I'm just going to rinse this out so that we have 2 cups of each, 2 cups of salt water and 2 cups of fresh water.
Very sudsy.
That's a clean cup right there.
This is fun enough to watch.
We would like to mention that the hose is courtesy of Jason Patel. So, you know, I could not have done this project without Jason. Thanks once again, Jason. You're doing great. All right, so we have our clean cup. We have some fresh water again, same as what we've been using. This is just right out of the tap. We're just going to split this a little bit. So, now when you're scuba diving, generally speaking, you have to wear more weight in salt water. So, what does that mean for the density of salt water compared to the density of fresh water? If you're more floaty, you're the same person, and you're more floaty in salt water. Is salt water more dense or less dense? What do you think, Kitty?
I think that salt water is less dense.
Salt water is less dense. Okay, well, let's find out. So what we'll do first is we have our fresh water and our salt water again in the blue, and we have our fresh water and salt water again right here in the blue. The first experiment, we'll pour the salt water over the fresh water. Now at first these things might mix and we might have to have them sit for a little bit, because remember, these are both water. But because this has so much salt in it, it shouldn't necessarily mix as easily. And if it's less dense, as Kitty's predicted, it should tend to stay on the top of this water. I'm going to add a little bit more just so we can make sure we see that effect. Okay, so again, pouring salt water on top of fresh water, we should see, if Kitty's prediction is correct, that salt water is less dense.
I'm so nervous. Or I didn't make it strong enough and it will mix.
Why don't we let that sit for a little bit? So I'm going to put this one off to this side and see how well it sits. And this one, I'm going to add fresh water to the salt water. Is it working? You might need a little bit more intensive of food coloring to see the effect. Again, because these are both water, they will tend to mix. So why don't we set these both to the side and sit, and we'll move on to our next activity, and we'll check on these in a little while.
Science doesn't always happen perfectly.
I mean, there's a world where scientists are more prepared, and they do these activities in advance so that these things are ready. And we're not those scientists. So, now what I want to get into is discussing ways in which we use oil and water all the time in our everyday work, play, pretty much anything you can think of. So, Kitty, can you think of one way that we use oil all the time?
Cooking.
Cooking. Cooking's a great one. We use oil to, coat things and things like that. You think of another thing we use oil for? I'll give you a hint. It's really important right now. What do you think?
What are we using oil for right now? What do you guys think?
I think it's a trick question because a lot of times it can be both solid or liquid, but it is an oil.
Gasp. I don't know.
What we use all the time, and in fact probably more than anything right now oil for, is actually washing things. You remember right earlier when we used that dish soap, which is an oil, to dissolve that grease and kind of bring that density down. Oil does a really good job of removing things from water.
Huh.
So, this is all the more important than what we use as soap, right? Soap, even though it's solid in its natural state, is a form of oil when it's a liquid.
I did not know that.
And I want to demonstrate why that's important and why, especially right now, we're talking so much about using oil and soap and washing your hands very constantly. Let's do a smaller container for this, I think. Otherwise, you're not going to have any spice. You know, if nothing else, if everyone's just playing along with a bunch of water like I am, it's a pretty fun time. So, we have water, just in our little tray here. We have ground black pepper that we're using here. And you can think of this as kind of stuff and particulates that might be in the water. It's going to be spicy water, as one of my friends, Carly, would say. Now, all of this is just kind of floating on the surface. You know, we can kind of mix it around a little bit. Let's grab one of our toothpicks. You know, there's some on the bottom. You get a good shot there. Right? And now, if I were to stick my hand in that, what do you think will happen?
I think the pepper is going to stick to your hand.
Yeah.
Should we try?
I think we should try.
Gasp.
Right? Mm-hmm. And now, so the pepper, what's happening here is the water is sticking to your hand, the pepper is sticking to the water, and so therefore it's being stuck on your hand. So you want to try and get that off, Kitty?
Yeah.
Just like...
Nope.
Maybe try wiping some. Still got some on, huh?
Yeah.
Yeah. Well, this is a big problem, right? If we need to get something off of our hands that's staying in the water, I'm just going to add a little bit more so we can see. One thing that can be really helpful is oil, because the oil will stay on our hands better than the water will, because we have lots of oil on our skin. So, if I, for example, maybe take a little bit of dish soap, just a little bit, not much. I put it on my finger, and I put my finger in that water. Now see, what's happening here is, remember how that dish soap won't dissolve into the water. So it's actually just spreading out all along that surface. And because this pepper is stuck to the water, it's not going into the oil. And so actually, if we use a little bit of oil on our hands that have our pepper on it, and we coat our hands in that oil, a little bit more, and then we rinse with our cucumber water. Just kidding, our Clementine water. You'll see that my hand's now totally clean.
Perfectly clean.
It's still, it's in fact still a little bit oily, so I'll just use the hose here for the rest of it. But we see the idea that, in fact, without oil, we will never be able to clean our hands properly. And this is why it's so important that we're washing our hands with soap and water and making sure that our hands are totally coated in that soap before we rinse it all off. Kitty, would you like to rinse your hands?
Yeah, I would love to. I still just have pepper.
You need some oil.
Oh, that's right, the oil. Now, I am holding the phone, recording, so this is not an effective way. Oh, thank you, Joe.
Mm-hmm.
So, totally coated between your fingers, on your wrist. Who knows where the pepper got?
Right? And so this is why what you're hearing a lot of right now is to make sure that you're washing your hands for at least 20 seconds every time you wash your hands, because that gives you enough time to make sure that oil and soap is coated everywhere on your hands. Okay, well, I think that's all the activities I had. Were there any additional questions?
Any questions out there, guys? Thanks for those of you who have stuck through the whole thing. I would like to send a special thank you to my other guest scientist today, Wednesday. Wednesday uses water. This is Wednesday, by the way.
Wednesday, it's Science Saturday.
Hey, Wednesday.
Wednesday uses water all the time, right? Just so that she can grow big and strong.
Yep. All right. There we go. Well, thank you everyone for joining us today and for those who will be joining us recording later. And stay safe, wash your hands, and have a happy Science Saturday.
Bye.
Bye.